Welcome to the recap video of our edge detection in Verilog project. The purpose of this video is to recap how our modules work and provide a demo. So starting off with the background and motivation, edge detection highlights the region of an image that contain a high gradient between adjacent pixel values. It can be an important step in computer vision and machine learning algorithms, basically allowing the algorithm to discard the non-important parts of the image. And also the output will be smaller in size than the original input, which helps to save on storage. So giving a brief overview of the phases of our pipeline here, it starts with transmission, where we break down the image and send it through the UART port to the FPGA. Then we perform processing on the FPGA side with our RGB to gray module and our Sobel algorithm. And then finally we transmit back to CPU side with the UART port again, and also display to the monitor using VGA. And just a basic overview of the pipeline in graph form, you can see on the left the Python modules and on the right the Verilog modules. So starting off with our pipeline is the transmitter on the CPU side, which will send to the Verilog side.
Hello, this is Xiteng Yao. I'm going to talk about UART communication in our project. UART communication is short for a universal asynchronous receiver and transmitter. UART is basically two wires communicating with each other between two devices. One is RX, one is TX. So TX is responsible for transmitting data. RX is responsible for receiving data. And they work together with a special pattern. The first signal of a UART communication is always 0. After that, there are 8 bits of signals containing data. And then the last bit is always 1. So both transmitter and receiver can know that how to communicate with each other. UART in our project is responsible for sending the image to the FPGA and receive it back after the processing. The receiver is designed as a state machine. It first waits for the pattern of the signal and starts the receiving process. Then it receives 8 bits of data during RX data state, and it finishes and waits for the next pattern to be detected. Similarly, for the transmitter, it first waits for the input data to be valid, and it starts the transmission process. It sends 8 bits of data in TX data process, and it goes to the next state until finish, and it waits until the next data is valid. This is an example of using UART in our project. Whatever I typed on the PC side is transmitted to the FPGA, received by the receiver, and transmitted back by the transmitter.
And now we will discuss the parser module, which comes after the UART receiver. The parser module allows us to rebuild the transmission over the UART port to the FPGA. So as you can see in the diagram here, we'll receive byte by byte from the receiver. The first 4 bytes are reserved for the height and width, where the first 2 are for height and second 2 are for width. And then the parser expects the image data to come in RGB format, one after the other. So the parser allows us to extract the height and width, and then also sort of stack the RGB values so that the downstream modules will receive them at the same time, obviously on a slower clock. And what you see in this next slide is 2 snippets of code from the parser module, where you see we have a counter as data is being received. So the first 4 bytes are for height and width. Once the height and width bytes are received, the rest of the bytes are considered RGB data. So as you can see in the code snippet on the right, the data will be gathered in output at the same time to the downstream modules.
I will explain how we convert the color image to grayscale and design the Sobel algorithm. First, we have an RGB to gray module, which is streamlined, meaning that as it's receiving the color input, it outputs its grayscale. Then we have a module called Rumble-like. This module is a memory manager that receives the output of the grayscale module and stores it in the correct address on the VRAM memory. And whenever the Sobel module needs it, It reads the data from the correct address and provides it as output of the Sobel module. We have used Xilinx IP4 VRAM, which you can observe instantiated here. This is a Sobel module, which has two pairs of the counters for addressing the width and the height of the desired pixels. One is designed for pixels in the image from top left to the bottom right, and the other for addressing the 9 pixels around it. This algorithm has two 3x3 filters that needs to be convolved with the image. To achieve this using the mentioned counters, it moves over the image in 9 clock cycles, reading a 3x3 matrix of the pixels from VRAM. In the always block below, it convolves them with the filters, and the output of the algorithm is sent to a transmitter module for transferring to PC and VGA module for displaying on the monitor.
Hi guys, please let me introduce our VGA module. These are all the input-output ports. This is clock. The transmit value is only for test. VRAM input is we're actually first we use the first part of our program to generate a grayscale image with the Sobel algorithm, and then the second part is our VGA module, which reads from the VRAM and output to the monitor. So these are so I use this codes to set the frequency for the monitor, because this is required by the monitor. And this is intrinsic frequency. You can see I use this frequency all over here. And this is a horizontal count, and this is a vertical count. This number is basically coming from come from VGA signal standard timing. You can see here the whole scan line for horizontal timing is 800. The whole frame for vertical timing is 525. So this is required. You can also see here the synchronization signals should be the same with synchronized paths. And then we assign like these colors to this region, which is our resolution. So that's all. Thank you.
This is how we do our test bench. When the FPGA are unavailable, we start with an image. We convert it to byte data like this. The first 4 bytes are the dimension bytes. The rest are all the pixels. And we inputted it into a FPGA test bench using the reading image, and the test bench will be able to read in the data, do the process, and transmit the data back. We write that into another file, and we are able to reconstruct the file into using Python code, and the result is like this. This is an example of using our code on a real FPGA. First, we need to program the device, then press the reset button. After that, we need to transfer the data from the PC to the FPGA. The yellow light is the data transmission light. Then after a while of Sobel processing and data transmission, the process image will be displayed on the monitor. The image shown on the monitor now is the Sobel edge detected image of iguana. This demo shows that our design is capable of receiving data from PC, do necessary transmission and preprocessing for it, and then conduct a Sobel edge detection on it and display the results. This satisfies all the goals we set at the beginning of the project. Thank you very much for watching our video.